We're going to talk about nuclear reactions and what is the essential idea. That's what I just said before. It's that energy can be released in nuclear decay as a result of the equivalence. We talk about the mass energy equivalence between mass and energy. We're also going to introduce a new unit for mass. Well, it's not new, it's new for you. Because we're dealing with such small changes in mass, we use a unit of mass called the unified atomic unit. And its symbol is little u. And 1 u is equivalent to, let's see, you don't have to remember this, it's in the data book that you were given in the exam. It's a very small number, and you have to use all the digits if you're going to use this in calculations. 1.660540 times 10 to the minus 27 kilograms. Why have we chosen this particular amount? Well, it's just a standard, and it's equivalent to 1/12 of the mass of a carbon-12 atom. That's just a definition. Right, next we're going to talk about the concepts of mass defect and binding energy. Later on today we're going to talk about something called mass difference. It's important to distinguish between mass defect and mass difference. Mass defect is a property of the nucleus, whereas mass difference is properties of products and reactants in a nuclear equation. So these are properties of a nucleus, if you like. So if you remember from Dora and Diana's talk the other day, in a nucleus we have, for example, a helium nucleus. We have 2 protons and 2 neutrons. Normally they would push each other apart because they're oppositely charged, right? We've learned that oppositely charges repel. but there's a force binding them together. What was the name of that force, Diana? The strong nuclear force. There's a force holding them together. So in order to pull them apart, what do we have to supply? What do we have to give the system? Energy, right? So in order to pull the whole thing apart, we need energy. So energy needed, underline that, to separate protons and neutrons. And conversely then, if we take individual nucleons and join them together, what do we then get? Right, energy would be released. So let's draw another. Let's maybe make it a bit clearer. So in this diagram, to pull them apart, we need energy. Let's draw another diagram underneath. Let's have them all far apart. We draw them, pull them into the center. To make a nucleus, we get energy and this energy from either of these two, the energy needed or the energy released, is given by energy is equivalent to the mass defect times the speed of light squared. This is the mass energy equivalence. So it actually turns out that if we were to weigh the mass of a, for example, helium nucleus, and then we were to split it up and weigh the masses of the two neutrons and the two protons when they're actually apart, the mass of the bits when they're separated is less than the mass of the nucleus itself. The mass has been converted into energy. No, other way around. The mass of the protons and the neutrons separately is more than the mass of the nucleus. And that's what's called mass defect. Okay, let's take a new slide. Let's just save that one. So the mass defect, sorry, is the difference between the mass of the separate nucleons, neutrons, protons, minus the mass of the nucleus when it's together. So let's do a quick worked example for this. Take helium, which has 2 protons and 2 neutrons. So the mass of the helium atom is, now we're working in unified atomic units, U, 4.0026 U. Now this is the mass of the atom, atomic mass, but we're working with nuclear mass. What do we have to subtract from this mass? Mass of the electrons. The electrons have a small mass. It will be 4.0026 U minus 2 lots of, and the mass on the electron in unified atomic units is very small, 0.000548 But when you're doing these atomic calculations, always keep as many significant figures as they give you when you're working through, and then if you asked to round up, round right at the end, because it's quite a great overassumption if I was to round here, for example, to one significant figure, because it's such small changes in mass. Because mass is energy is equivalent to mass times the speed of light squared, any tiny change in mass is going to give us massive amount of energy and very big inaccuracies when we're calculating. So that's why you should always keep them there. That gives me, finally, if you just do the maths, 4.0015 U for the mass of the helium nucleus. However, if you just add 2 lots of a mass of a proton separately, 2 lots of a mass of a neutron separately, 2p plus 2n, the worked examples in the book, you actually end up with 4.0319 U. This value is bigger than this value. So the mass defect for helium, you get different mass defects for different nuclei. Sometimes it's given the symbol delta is this thing minus this thing, which is, let's see, 4.0319 minus 4.0015, which is 0.0304 U. So that is then equivalent to a certain energy, and that energy is the energy either we need to pull apart the helium nucleus, or the energy we get if we were to form the helium nucleus from 2 protons and 2 neutrons separately. So that's mass defect. Difference between mass of the nucleus and the mass of its constituent parts. Oh, it's gone blue. My goodness. That's not good. Oh, I think my computer's dying.